record. Okay, I think we can start our class. Okay, now let's go to our notes. Okay, last discussions we are having the triple integrals in the spherical coordinates. Okay. So as you can see that we have now having a new coordinates that is called the spherical, and we can also convert our traditional rectangular xy and convert it into our spherical, which means that if we have xyz, we could transform or convert to rho for the radius, and then the theta, the angle theta, and then the angle phi or sine. Okay. And here's the conversions. Okay. And from here, what I would like you to observe is how do we interpret the triple integrals in the spherical coordinates. So I think we can start giving you the subject. Okay. You crop this. Let me make it bigger. Okay, now if we observe, okay, and let the E, okay, as our the total sphere that we are going to observe, let's say it's E. And we define all the terms, AB for radius, and then alpha, beta for theta. And C and D for the angle phi. Let's say this is our interval, and if we slice, okay, if we slice this the sphere, if we slice and take just a small pieces, okay, so we slice using some delta in the radius here, the delta rho. We have also the delta of phi and the delta theta. And perhaps it's not really clear what's going on here, but let me just go through the projections. So if we project this, so take this as a projections, we might have the side view and the top view. Okay, if we look here, it's clearly can we see that this will be the arc, right? The arc length, the arc from the circle. For this from the side view, the red color, and for the green one at the xy plane, we see that we also have the arc length, and we have the radius and then sine sine. Okay, this is from this line. Okay. This is basically a similar triangle from our triangle here, from here. So we transform into, we slice into small pieces, and we could directly calculate the volume, okay, the volume of these small pieces. So if we would like to compute, or let me just write the delta volume, that is the small pieces, the volume of the small pieces. So delta volume IJK, this is delta rho multiply with the rho I delta phi, and then multiply with the rho I sine k, and then delta of theta, which means we are going to multiply this row, this, and this. Okay, we multiply this volume of the rectangle. So we treat this small pieces from our sphere as a rectangle. So that's become our delta phi. So let's compute and let's simplify this delta phi. This will be rho squared and a sine, and then writing all the delta. Okay. Okay, now from this delta, we could then write down the formulation for the volume in triple integral for a function. Okay. So let a point, okay, let's say that the point xyz as a sample point. Let this be rectangular coordinates. And this rho, and then theta, and then phi is points on the solid E. Okay. So we could write that fx, yz, d phi is equal, and we are going to express in the Riemann sum. So take the limit L, M, N. They are going to approach infinity. And take some the sample points inside. Okay. Now these expressions we can transform. Okay, from x, y, z we can transform to the spherical. Okay, so we can transform to the spherical. Okay, we transform. X will be, it's supposed to be r cos theta, so but r we transform to the sphere, becomes rho I sine psi k cosine theta j, and then the y will be for rho sine psi k sine theta j, and this will be rho I cosine psi k. And the delta phi, I think we can move a little bit here. Now delta phi, we are going to take in the rho I squared sine psi k delta rho delta theta delta psi, and that is the Riemann sum for the whole function. And now we can conclude from here, because it seems that we can correlate this Riemann sum with triple integral. So we can write now that the triple integrals of E of the x, y, z dv is equal so let me convert all to the theta, psi, and rho. Okay, so that's the spherical where the E defined by okay, now this is the triple integral for the spherical coordinate. Okay. So the idea behind this spherical is first, later on we need to define or we need to observe how we can convert some integrations that we have in xyz and we convert to the spherical coordinates. There is some obvious reason that we are going to look at. One thing that is obvious is from the sphere equations. For example, sphere equations, we have x squared plus y squared plus z squared, right, equal rho squared. So whenever you find this, or anything that is you can correlate with the sphere equations, probably if you convert to the spherical coordinates, okay, the integrations might be simplified. Probably it will be easier to convert. Okay. Okay. I think just focus on this last message here for the triple integrals in spherical coordinates. I think that should be enough to understand at least how we are going to move forward. Okay, if you have any questions, you can write in the chat box if you maybe want to discuss something. And also, I forgot to mention that we could also see directly the dphi from this subject. Okay? So we could just see we have the rho, the delta, the small pieces here, and we have the delta theta, delta phi, and multiply by rho. So we could just multiply all of this, okay? And then this will be also dphi. Or we could just write it should be delta. It should be d. Okay. Okay, I think we can move to the next page. I would like to just to add some notes. Okay. The formula can be extended, and we can write E as let me write again. Okay, let's say the alpha is for alpha, beta for theta, C for psi, and we could have a function of two variables of theta and psi for rho. This could happen, and this become our upper and lower surface. Okay, if you still remember what we did in triple integrals last week, we have upper surface, lower surface. This is basically similar to that notion. Okay, for example, we could also look at this example. Find the volume of solid lies above cone z equal square root of x squared plus y squared, and below sphere x squared plus y squared plus z squared plus equals z. And if you would like to see how it looks like, this is the sphere and the cone. Okay, so we need to find the volume. Okay, so we have a cone, we have a half sphere. Now what do we do first? First, we could see that this is our sphere equations. Okay? We could start with taking this sphere into observing how the sphere is exactly going. Is there any shift in their center? Is there any change in the radius? Okay. So for example, if we take the complete the standard form for the for the z squared minus z, then we could have z minus half, right? So we should have 1 over 4. Okay, this means that the center is 0, 0, and half. So this in here, this is the center, this is 1 over 2, okay? And then here is half, 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 so the radius is half. But if we take a look our equations, these two equations, we could take these equations and write down that since we have the equations for the sphere, the basic equation is equal to rho squared, right? And z is rho cosine psi. So we could write rho squared is rho cosine psi. We have this equation. So rho is actually cosine psi. So actually, we can describe our radius in terms of function of psi. So we could say that our rho is a function of psi. In this case, it's a function of psi. And then we could describe the cone. We could describe the cone as z is rho cosine psi equal, and we could take the square root rho squared cosine squared psi, and then sine, and then cos squared theta, and plus rho squared sine squared psi, and then sine squared theta. And this will be equal to rho squared sine squared psi. And this will be equal to rho sine psi. And we could take the tangent psi is equal 1. Or in our case, this should be equal to pi over 4. Right? As mentioned in the picture here, it's pi over 4. Okay. And then we can write the descriptions for the interval as E. So we write all the possibility. So the theta for the whole full circle, the theta is from 0 to 2 pi. And then for phi, for psi is 0 to pi over 4, right? And then what is happening for the radius? Now the radius is from 0 to the cosine sine. This is because the rho we can describe as a cosine sine or a function of sine, because we know also the sphere is already shifted, right? The sphere already shifted, so we cannot really write down a sphere from 0 to some constant. So we should have a function, right? Okay, now we could write down the volume then. This will be from, since we have the theta that is, I think, not related with the other two variables, so we could write as outside integrations, and we could write the second one is the psi, and the inside integrals will be the rho, and we could write rho squared sine psi. This is the rho, the psi, the theta. Okay. Right, the outside integral, because there's nothing inside for the theta, so you could just take 2 pi, and then this part for phi, and it should be having because there's a cosine, not rho, sorry, cosine sine. So we should start from the inside. So we could have rho cubed over 3 and the sine psi. Okay. And this part will be rho cubed need to substitute first. So cosine sine. So cosine cube sine psi over 3 d sine. Okay. And we could start with substitutions. Use substitutions. So we could start with this is cos theta, and du will be minus sine theta and, oh, not theta, sorry, sine. And we could solve this, right? We could solve this integration, and we could write down this become minus cosine with power of 4 and 4 because it's u cube, right? It's u cube. So u cube integrate this become this, right? Okay. And then plug in 0, pi over 4. And this is seemingly going to have pi over 8. That's the one example on the sphere. Okay, perhaps any questions if you have something to discuss? Okay, if not, let me give you one more example, and I think we can move to 15.9, the change of variable in integrals, or Jacobian formulation. Okay, any questions? No? Okay. I will move to the next page. If you would like to take notes or take screenshots, you can take screenshots. Okay, let's move to the next page. Let me check. There's no picture, but let me just let me go to the other notes for the other class. Let me just take the picture. Okay. Just for a moment. Okay, this is the picture. Okay. Okay, let me view the picture. Okay, what we are going to evaluate is we are going to evaluate this E f x y z dv. So the f is this one, the function. The e is according to this region. Okay. Now we have a new perspective now with the spherical. Okay. And to give you a context, like how we solve this these questions. Okay. First is we are going to observe the region E. Okay. The region E is perfectly, we say, you have a ball. Let's say you have a ball. You cut into half this ball, and then you have this sides, right? And then you cut another half, okay? And this is becomes your E, right? Okay, that's how we can get this the shape, the cutting. And now if we look on the sphere itself, we have two spheres, right? We have sphere with radius 2 and radius 3. This is radius 2 and radius 3. At least we have the row is between 2 and 3. Okay, so that's for row. We have the results. And now for the theta and phi, this is a little bit complicated if you are missing out on the polar. Right? But if you take, for example, the phi will start from here. Let me write with the green color for phi. So this will be phi equal 0. Okay. And this phi is equal, sorry, not theta, phi equal pi over 2. And this one is phi equal phi. And we have only until pi, right? Because basically this phi will be having another rotation for theta, right? I hope you understand my words, but this is the angle is here, okay? The angle. So according to what we have here, this psi is from pi over 2, okay? From pi over 2 until pi. So just this, okay? That's our the phi. So we can write down the phi is from pi over 2 to pi. Okay. Now the other one, the theta, is in xy plane, right? Okay, let me write with the red color. I hope you can make a distinction between the green and red. So in the theta, okay, let me write all specific theta, okay, like that. So theta is let's say the theta is yeah, the theta is from supposed to be from pi over 2 to 3 over 2 pi. So if you look here, this is 0. Oh, no, not 0. 0 is, I think, from here. Because this is pi over 2. This is pi. And this is 3 over 2 pi. Yeah, I think this is better perspective. Okay. So we get pi over 2 to 3 over 2 pi. But since I think because this will be symmetrical, okay, this is will be symmetrical with the other sides, I think in the calculations they should be having same results, okay, because of the symmetry. I believe so. And then the triple integrations will be, this is pi over 2, pi, and then pi over 2, 0 over 2 pi for the theta, and then 2, 3, and inside this is equal rho squared, square root, and then this become rho. So it will be rho, and then multiply with rho squared sine phi d rho d theta and this. Since all is constant, we can separate each variables. So we can have okay, so this will be negative cos theta. This will be 3 over 2 pi minus 1 over 2 pi. This will be pi over a rho with power of 4. Okay. And this will be pi. This is 1 pi, and this will be 81 minus 16 divided by 4. This will be equal to 65 over 4. Okay. So I hope you get the idea for determining the angle, okay, for the theta, for the psi. Okay. Okay. Any questions? Any questions regarding this explanation? Okay, I think we will have more practices later on when we finish all the sections in chapter 15. And also, I plan to add more additional videos, especially for triple integrals, and including the cylindrical, the spherical. Okay. Okay, if there's no questions, I would like to just continue. This lecture is 15.9. This is what we call the change of variables in multiple integrals. Okay, to begin this section, maybe we can recall the calculus 1 method, which is we learn about the u substitutions, right? U sub method. So if you have integrations from a to b of fx dx, we can convert this with another variables we call the u. Usually we call u. Okay. Where the x, okay, where x is g of u, or we can also write that a is g of c and b is g of d, right? Or we can write in terms of the differentials. So f of x, no, f of x of u, okay, and then dx over du, and then du. Okay, perhaps the last one is the preferable method that we are usually using in chapter 5 in integrals, right? Okay. So this is a change of variables in early chapter of calculus in calculus 1, right? Now, how we can make the change of variables in double integral? So change of variable in double integral. Or let me just, I think we can just cut this and write in the next page. Okay, let me move to the next page. Okay, recall the 15.3, the polar coordinate, right? The double integral in polar coordinate. We have the double integral and function of two variables and the a, and we convert, let's say, from R to another new region of polar, and we convert x into R cosine theta, y into R sine theta, and this become R dr d theta, right? Whereas, okay, S is the region in a new plane, okay, R theta plane. It's not the same with the xy plane, right? But it corresponds with the xy plane. It's not the same, but it's correspond, which means we can convert them. Correspond to R in xy plane. So in general, we can consider a transformation. Consider transformations. Transformations D. From UV plane to XY plane. Okay. Let's say we are going to convert UV plane, so it's another plane, to the XY plane. Okay. And we are not sure what's the correlation between this XY and UV, but somehow we are going to correlate these two. So we write down the transformation as T transforming the UV, and it's become XY. This is how we can write in terms of mathematical notation. Okay, where X and Y are related to U and V, and the relations are that X is a function of two variables, UV, and Y also function of two variables of UV. Or we can also sometimes write as X UV, or Y UV like this. Okay, both correct. It's okay to write both equations like this one. And assume that T is C1 transformations, which means that the function g and h are continuous, okay? Or it's having continuous first order partial derivatives. So there's not a problem when you try to partially derive. So the transformations in our sense, to describe this mathematical notations is it means that it just functions that all its domain and range is on the subsets of two-dimension R, and then we are going to uh, mirror or not mirror to place all the points. Let's say you have u1 v1 u2 v2. We are going to place into a new subset of x1 y1. Or if we are going to describe in a more general way, we could describe that from uv to xy, we are going to have a transformation t, which means this is practically, this x1 y1 is an image of point u1 v1. So practically the R, and we call the R, the region R, is basically an image when you transform uv to xy. And if the transformation is one-to-one transformation, then it has the T inverse. So we could write down that U also having connections to the function of two variables x1. Let's say we have G because we have the inverse, and we have the V is H x1. Okay. So let's say to give you more clear explanation on how the transformation might happen in some plane. Let me just give you a visuals later on the next page. But here is just an introduction that we might have transformations that is pointing out from one point to another point, and we change into the different plane. We project into different plane. I think that's better words. Projections. We project some points into another point in different plane. In different plane. And how we are connecting these two planes is from some relation, which means the first one is having the x is having a function of two variables uv, and then if it has an inverse, if it is one-to-one transformations, then we could have the inverse of t, which is we can write u in function of two variables xy. Okay. Now from here, what we are going to do is we are going to do some simulations. How to transform? Manually transform. So let's say we have x example. We have x defined by u squared minus v squared, and then we have y is 2uv. And then find the image of the square uv, so from 0, u1 from 0, v1. Okay, so we have a square, and we need to transform this square using these transformations. Okay, these transformations. Okay. So this is the relation between x, y, and then u, v. Okay. Okay. Now we have the square. Uh, so it has. Let's say we are defining all the vertices. So the vertices for UV is from 0, 0, right? And we have also the vertices for 0, 1, 1, 0, and 1, 1. So we have a square by 1 multiplied by 1. Right? So we could have UV plane. Let's say this is or UV plane like that. And we have this is 1, 1. So this is our square. Okay? This is our square. So this will be 0, 1, 1, 0, 0, 1, 0, 0, and 1, 1. Okay. Okay, let's name all the sides for this square. Let's say this is S1, S2, S3, and S4. Okay, let's start. Imagine we moving from this origin, we move here. Okay, we move there. So according to this image for the square, when we move, this is when we are having the v is 0, right? We have the v is 0 and u will be going from 0 to 1, right? And we have the equations. Let me write here, x is u squared minus v squared, okay? And by doing so, by these restrictions, then we have x equal u squared and y equal 0. Okay. And by doing this, we could see that from x, okay, that we can describe, because u is from 0 to 1, x is from 0 to 1. Okay. So we are going to map the S1 as just a line segment, from x equal 0 to x equal 1. Okay. So this is S1. We are going to see the clear picture at the end. And later on, we move to S2. S2 is S2 is mapping from u equal 1, and v is changing from 0 to 1. Okay. Maybe let me write S1 here to make it clear, and S2 here. And by doing this, we are getting the equations is 1 minus v squared, okay? And y is 2v. And then if we take this as y over 2, and then we could write the x as 1 minus y squared over 4. Okay. And also from here, we could see that this x will have interval from 0 to 1. Okay, and since we already have this equation for x, we are going to have a parabola, right? We have a parabola from 0 to 1. Okay, so we have this parabola, and the parabola will move, or will be drawn from 0 to 1. Okay, and similarly, S3 is this part, is going to change the u from 1 to 0. Okay, so this is v is 1, and u is from 0 to 1. And we have similarly, this becomes u squared minus 1, right? Or we could write down, if this is to v, sorry, 2u, and this will be y squared over 4 minus 1. Okay, now since we have this, because we have this minus 1, now we could see that the x is going to have interval from -1 to 0 for S3, and we have another parabola. Okay, we have another parabola with this interval. Okay, and lastly, the S4 is going to have the same. The u will be constant. Then v is having changed from 1 to 0. So u will be constant 0, and v is from 0 to 1. So we could see from the connections, this will be minus v squared, and y is equal to 0. So we are going to have -1, x, and then 0. And if we are going to transform this, probably what we have, so if we move from this origin, going to S1, S2, move here, then we could have, first is we are going to move from 0 to 1, as mentioned in this part. So we are going to move here, and then the S2, we have a parabola. This is the parabola. So this will be our next destination. This is S2. And S3 is another parabola, and this will be around here. This is -1. And then the last one will be from -1 to 0 from here. So this is S1, S2, S3, or if sorry, S3 is here, or this is the image, or the result of transformations from S1, S2, S3, S4. Okay, or maybe I will just take the results directly. Okay, that's how we are going to have a transformations. Okay. Okay, is there any questions? Okay, I think we can move to another one. Okay, now let's see um, in more details what will happen in the double integral. In the double integral. Okay. Okay, in the double integral, if we take the illustrations, let's say we have a plane of B, U. Let's say we have, an S. Let's say we have delta V, delta U, and let's say we have U0, V0 as this point here. So this is U0, and this will be V0. And let's say we have a transformations. We have transformation. And let's say we have y and x as our usual rectangular coordinates. And we have, let's say, as like this, and we call this is r. And this will be x0, y0. And to describe these sides, we are going to use the vector function. So this part is a vector function of u0 and v, and this part is u and v0. Okay, we could write the image of S is a region of R in xy plane. And the boundary is by these transformations. And we could have the vector position for UV. So each side will have a function of two variables UV. So this vector is vector positions of the image of point UV. As you may see, that the equations of the lower sides will be the phi0, the lower side here, this one, right? Phi equal phi0, and we have the so when this phi0 here, this is correlating with the vector functions, this vector functions, and this vector and this u0 will correlate with this vector functions. Okay, and now the tangent vector. So the tangent vector at x0, y0 to the image curve is, we could take the partial derivative. So r, we write ru, so partial with respect to u. So this will be g u u0 phi 0 I plus h u u0 phi 0 j. Or we could write this as dou x dou u I plus dou y dou u j. And we also have the r phi, but partial with respect to phi. Similarly, with phi, we have dou x dou phi for I and dou y dou phi for j. Okay, we have these two partials, right? And then what's next is we are going to approximate. Okay, we are going to approximate this r. Okay, we are going to take it into a factor that we need to define. So if we want to write down, it's supposed to have like this. Okay, not really a straight line. Okay. So we take this in a new definitions for a vector. So let's say this is our r, okay, and this is our starting point. This is the starting point, and we could define a vector b as this vector positions. So it's changing this phi because we have say that it's correlate with this phi here, and it's correlated with this u for this u0 and phi0. So we could say that phi0 plus delta phi and u0 plus delta u. Okay. So we can write down that vector A is r u0 plus delta u minus r u0 phi0, and vector B is plus delta phi minus r u0 phi0. And then according to the limit that we have in the past, right, that ru is by definition is a limit when delta u is approaching 0, all this r u0 plus delta u phi0 minus r u0 phi0 divided by delta u. Okay, this is by definition. And r phi delta phi and by these two limits we can approximate that R U0 plus delta U phi0 minus R U0 phi0 is equal to, or approximately equal to, delta U RU, and the second one R phi0 plus delta phi minus R U0 phi0 approximately delta phi and R phi. Okay. It means by doing this, since we approximate the this with a vector a and b, and also we are having this limit definitions, we then can construct a parallelogram from this delta u ru and delta phi r phi. Okay, so you can construct this parallelogram. So what we are approximating the area. So we can approximate area of R. Okay. So area of R with this parallelogram, we can have the cross product, right? The area of R is cross product of the delta U RU cross the delta U delta phi R phi. Or we could simply cross product RU R phi and then delta U delta phi. Okay, now we could construct this cross product using this partials equations. Okay. Okay, let me just take times, give me a few minutes for writing these notes. The important note is to is the parallelogram, okay, and then the approximations, okay, the limit definitions. Okay, let's go to the next page to construct our cross product. Let me write the RU and RP is both described in the partial descriptions. Okay, these two RU and RP, and we construct the cross product. These two cross product. we construct this. Okay, I think this is okay. So if we see from here that since k is 0, we could just write the cross product as the determinant of this dou x dou u, dou y dou u, dou x dou phi, dou a dou phi, and multiply with k. Or we could shift this the other sides. Should be the same value. So shifted this too, just to make sure that this is the same. Okay, these two are the same. Why switching these two? Because it will be creating a pattern for you to write a general formula for. We call the Jacobian formula later. Later on, we call it Jacobian formula. Okay, so definitions. Okay, from here, the Jacobian transformations. Jacobian of transformations T given by x equal g of function of u and v, and y is h, u, and v, is we write the Jacobian as dou x y dou u v. Okay, so we transform this based on this determinant. Okay, and to help you to reorganize the structure, we need to make sure, but since we are writing the Jacobian as dou xy and u v, so we need to make sure that this is x u v y u v. Okay, and in practical, it's not too complicated at all. Okay, in the practical, but for just some proving, it's a little bit complex. Okay, we could write this as now back to the parallelogram. Okay, this is just the cross product, and the cross product itself we call as a Jacobian. Now back to the area of parallelogram here. This is what we are going to observe and to construct next. So the area, okay, or we can write down area of parallelogram as a delta A, since we are going to make it the small pieces one. So this will be constructed as the Jacobian multiplied with delta U and delta V. And Jacobian is evaluated at some point U0, V0. And now we are connecting this Jacobian with our double integrations. Okay, double integrations. So we are going to take small pieces. Okay, between this S and R, the previous picture. So we take the delta U and delta V. Okay, in S. Okay, we take this delta U and delta V, And we also take the R, okay? We take the small pieces and make it into the area of parallelogram that we already construct. Okay? And now we can take the Riemann sum. Okay, we take the Riemann sum. For R, the Riemann sum we take the sum and we take y, xy, and delta A. And then we construct this Riemann sum and change x and y through the function of u phi, okay, function of two variables u phi. So f, this is becomes g, ui vj, and h, ui vj. And then delta A will be having the Jacobian. And then delta U, delta V. Or we could say that in terms of S, okay, when we transform based on the XY relation with the UV plane, we could have UV, H, UV, and then this will be the Jacobian, and UV, and this will be the DU, DV. So this will be a new definition in double integral. But this is supposed that the T, okay, the assumption is T is C1 transformation, which is continuous for first order partial derivative, whose Jacobian is non-zero. T will maps, or T maps S in UV plane onto R in XY plane. Okay. So this is in general a change of variables. So change of variable in double integral. Okay. Okay, any questions? Okay, let me give you an overview on how we are going to apply this Jacobian. The first example is the polar coordinate that we already have discussed. Okay, so if we convert the if we check this, okay, we convert and let the x is basically a function of, if we change to function of r theta, this becomes r cosine theta, right? And y also similarly, it's a function of r theta, and I'm writing it as g and h to make it similar with the previous one that we have discussed in an example with g and h, right? And let's say this is our transformation, so we need to transform, okay, from this s to r. Okay, we map all the uh, all the sides. Okay, how do we apply this? And we have uh, correlations between x, y to the r theta, right? Okay, we could start with the Jacobian. So Jacobian x, y to r theta. Okay, and we can write this dou x, dou r, dou x, dou theta, and dou y, dou r, dou y, dou theta. Okay, now we can take the partials from the x and y. Okay, we take the partial from the x, we take partial with respect to r. We are having the cosine theta. So, and we take partials with respect to theta for x. This is negative r sine theta. Similarly, here is sine theta, and this will be r cosine theta. Okay, we take this calculations. We cross multiply r cos squared theta minus r sine squared theta, or we just plus this too. So r cos squared theta plus sine squared theta, or this is just r. Okay. Now from the r, okay, that we have, okay, xy, we're going to apply into as f r cos theta, r sin theta, and this will be Jacobian xy, Jacobian r theta, and the r d theta. And we could write down, this will be alpha r dr d theta. Okay, so this is how we get r through Jacobians for the polar coordinate. So when you have the conditions or the correlations between this xy and, let's say, UV or any other plane, then you can start with the Jacobians. We start with Jacobians first. And why the Jacobians will be helpful? Because If you have the region that is probably it's a little bit difficult um, to compute, you can make some simplifications and take the Jacobian, and then you can transform the formula for the integration, and I think it will be very helpful. Okay, giving you an example. Okay, giving you an example. Use change of variable. Let's say we have this. It's the same object with what we have done. Okay. I think I can just take the image from before. This image. Crop this. Okay. So use change of variables. Okay. To evaluate the double integral YdA. R is region bounded by x-axis and parabola. It's the same parabola with this, but it's on a y squared 4 minus 4x and y squared 4 plus 4x, and y is in a positive number. First we could exchange this into 4 minus 4x. This is 4 plus 4x. We can exchange this. So why we are going to change the variables? Okay. It says that use change the variables to evaluate this double integral of r. If we try our best to integrate with r, what will happen here? Let's say we are going to have maybe from 0 to 1. And then we have the x, right? The x is from -1 to 1, 0, or maybe 0 to 2. Maybe 0 to 2. Let's say this is y. So the x dy, this is start from, this is y. 1 minus, or y squared over 4 minus 1 until 1 minus y squared over 4. We could try to solve this. Okay. I believe this, still we can do it, right? We can take x, y, and then take the integrations, blah, blah, blah. But since we have some clue here that we have these two function of u v. Okay. So let's just take change of variables first, and let's compare between these two. So first, take Jacobian. Take Jacobian. Okay. And let me write all the functions. X u squared minus v squared y equal to u v. Okay. Well, let's take Jacobian. X with respect to u, we take the 2u, this is 2u, and then this will be negative 2phi, and dy will be 2phi 2u. Okay. And this will resulting in 4u squared plus 4phi squared. And this Jacobian should be a positive, right? And then let me write a little bit, moving a bit upper. Okay. And then we could write down the r, and we can write the transformations and change to s. Y is 2 feet, 2u feet, right? Based on the informations. And we write in the Jacobian, and then state dA, and then is equal if we remember that s, okay, this s is a square with this distance, right? 1 by 1 square. So we could take that square, so 0 1 0 1, okay, and this will be 2uv, and multiply with 4u squared plus v squared from our Jacobian, and du dv, and this will be 8. And solve the integrations. U cube v plus u v cube. Okay, start with the u first. U will be u for v plus u squared v cube, and then take 0. So 1 over 4 v plus half cube. Okay, and then we have dv, and then again this is going to be v squared 8 plus v4 8. So this will be half plus 1 over 8, or I think I make a mistake. Wait a minute. V squared v4 half plus half plus 1 over 8. This will be 5 over 8. Is that true? Supposed to be 2. why my answer is 5. Well, let me just check. This is still having 8, right? So we could have, this is 2 phi plus 4 phi cubed. So this will be phi squared plus phi 4. Oh, yeah. Now it's true. 2. Okay. Okay, now it's correct. So it's equal to 2. Some one example. Okay. Okay, any questions? Okay, I think I will just pop until here, and we still have another example, and the triple integrals, the change of variables in triple integrals, and more on exercise and practice for Thursday. And we finish with actually the fundamentals. We finished the discussion. So chapter 15, I said is finished. So I would like to know, and now I would like to know our schedule. Our schedule. So this lecture stops until this one. Okay, this change of variables. We are continue a little bit next Thursday. But for now, let me just go through the schedule. So suppose we are having our Thursday class in 26th of May, right? 26th of May. We still have one class. And also next week, 31st of May. Yeah, 31st of May, we still have another class, but this class will be just a review. Okay, you can come, you can or not. It's okay if you feel you already feel okay with all the chapters. You don't need to come. Okay, uh, you can come you can come or not. It's okay. It doesn't have any additional chapters, but we will have some reviews. And this 2 more class, okay, until the end of the semester. Um, the schedule for a final exam. Perhaps we will have the final exam on June of 7 or June of 9. Okay, between these two. So I need you to make a decisions, and I will open a polling. So let me just stop the screen sharing for a while, and let me take a polling. Okay. Okay, please um, choose which dates. And I will announce one more time after this polling. Okay. So it seems almost 45% choosing or 50% choosing 9, I think. We still have 7 students left not answering. Yeah, I think I can say uh, through this polling, the winner is the 9th of June. Okay, 9th of June. So this will be the final exam. Okay, unless you have other schedule, but I think better to finish the semester before 10, right? Because I think 2nd or 3rd of June already holiday, right? It's supposed to be holiday, but we still have additional 1 week for just final exam. But since we are having online exam, so I hope it's still okay with you, right? Because you can still just go home if you want to go home and making the online exam through your home. Okay, and we still have also the quiz on chapter 14. Perhaps this is going to be from Friday night or Saturday morning. I will use the different platform. Okay, it's not the quizzes. I'm using the different platform for this chapter 14. That is supposed to be uh, checking also whether the platform is sufficient for you, uh, fine with you, and I need to check all the systems working or not, especially for the final exam. Okay. Okay. If there is no other questions, I think that will be the end of our lecture. Okay. QR code. Let me close poll first. Okay, that's the QR code. And if you have scanned the QR code, you can leave the meeting. So thank you for joining the class today. Yeah, you're welcome. You're welcome. Okay, so that's the end of our lecture.